Hello everyone, my name is Finding Pepper and welcome to episode 5 of the 3D Minecraft tutorial series. In this episode, we'll be adding terrain generation into our Minecraft game, allowing for huge worlds. We'll use code from my Perlin Noise tutorial series to do this, and if you haven't watched that yet, you should go and watch it now. You'll only need to have watched episode 1 and the first half of episode 3 for this tutorial. Before we get into actual terrain generation, let's fix a bug from episode 4. When exiting creative mode, the entire inventory is deleted, meaning you can't pick up any blocks. To fix this, let's go into the UI sprite under when C key pressed, and change the if statement here into an if-else. In the else, we'll put a repeat 18 and add the empty value to inventory. So when we're switching out of creative mode, we add 18 empty values to the inventory, meaning that those 9 slots can now be edited. Let's test that out. And yes, everything works well. Alright, let's now grab our Perlin Noise scripts. Import the file from midway through episode 3 into TurboWarp. This is from right before we switched to doing 3D stuff. Running it, you can see this is what we've got. Now, drag the whole sprite into your backpack. Make sure you're in TurboWarp because the normal Scratch backpack does not carry over to TurboWarp. Back in your project, drag out the sprite. Rename it Generation, and delete the Scratch cat. Apologies to all Scratchy lovers out there. Now we've got a little bit of cleanup to do in the code. Delete the 2 uses of the Draw World block. One when flag clicked, and one when I receive Draw World. Then you can delete the Draw World block. Also delete the 4 arrow key press checks. Next, let's modify the find point height block. Currently, we use the x and y variables to determine what point we find the height of. Let's instead add 2 new inputs to our find point height block, x and y. Also add these inputs to find point height at layer. You'll notice that the only times we use the x and y variables in that block, we multiply them by layer. So let's pass as inputs to find point height at layer, x times layer and y times layer. Then, in find point height at layer, we'll replace our use of x times layer and y times layer with our x and y inputs. Like so. Alright, let's talk about how we want to handle generation. Like we did with the 3D generation in the second half of Perlin Noise episode 3, we'll divide the world into small square chunks. At any given time, 9 chunks will be loaded, the chunk with the player in it and the 8 surrounding chunks, forming a 3x3 grid. When the player moves out of a chunk, they will be pushed back 1 chunk, and new chunks will be loaded in. This creates the illusion of moving into new area, but really they stay in the same area, just with different chunks loaded. To make this work, we've got to set up some variables. Head to when flag clicked in our main game sprite. The chunk x and chunk y variables from our Perlin Noise got carried over, and we'll be using those, though we should rename chunk y to chunk z, to better represent our 3D axes. Remember, y is vertical position. Make one new variable called chunk size, which represents how many blocks are in one chunk. I'll set chunk x and z to 10 each, meaning we start the game in chunk 10, 10, and I'll set chunk size to 16, meaning chunks are 16 by 16 blocks. Then set the grid width and grid depth each to chunk size times 3, because we have a 3x3 grid of chunks. We aren't making vertical chunks, so set grid height simply to 60. Finally, before we reset player and start our game loop, broadcast and wait 2 new messages. Setup and generate chunks. And these should be broadcast and wait. In generation, replace when flag clicked with when I receive setup, so we can better control when these variables are set. We're going to make 3 variables here, which will influence how our Perlin Noise generation is translated to blocks. The first is height modifier. This will determine how high or low our terrain can get. When the variable is lower, the terrain will be flatter. Next, make a variable surface height. This is the height in blocks that a 0 from find point height should represent. In other words, is the water level, or the average height. Set that to 30, which you'll notice is half the grid height. Finally, make the variable detail and set it to 128. This represents how many blocks are in one Perlin Noise grid cell. If you divide it by chunk size, you'll get how many chunks are in one Perlin Noise grid cell, which for us is 8. The detail and chunk size variables can be thought of as conversion factors between our 3 different coordinate scales: block coordinates, chunk coordinates, and Perlin Noise coordinates. Next, go back into the main game sprite and drag the fill grid block into the generation sprite. Do the same for get grid index of position. We'll be needing them for generation. Back in generation, let's organize those a bit and get out a nice shiny when I receive generate chunks. We'll start with the fill grid block to get a fresh empty grid in which to build up our chunks. Now we have 9 chunks to generate, so let's simplify things by creating a block to generate 1 chunk, which we can use 9 times. Call it generate chunk at, with 2 inputs, x and z. Run without screen refresh. All the blocks we make today will be run without screen refresh, by the way. We'll pass to this block the offset from the current chunk, so that's either -1, 0, or 1. And inputs of 0, 0 would represent the chunk the player is in, or in other words, our chunk x and chunk z variables. In generate chunks, we'll use this block 9 times. We'll start with inputs -1, -1, then 0, -1, finally 1, -1, then duplicate those and change the -1 for the z input to 0, like so, and then do the same changing the z input to 1. So this should give us all the different combinations of -1, 0, and 1. Make sure you've got this correct. Now it's time to code generate chunk at. Our Perlin Noise came with x and y variables. Let's rename the y variable to z, again, like we did with the chunk y. Then we'll use these variables to represent the Perlin Noise coordinates we're generating at. We'll start at one corner, so set the z variable to, and here we need to first get the coordinates of the chunk we're generating by adding the z input to chunk z. Then we convert from chunk coordinates to Perlin Noise coordinates by multiplying by chunk size over detail. We're going to generate the chunk 1 column of blocks at a time, so we need to loop over each of those columns. So repeat chunk size each time, setting the x just like we set z, but making sure to change z to x and chunk z to chunk x. Then again repeat chunk size, so this will loop over every column or stack of blocks. Inside the inner loop, we'll want to increase x. We want to move by 1 block, but in Perlin Noise coordinates. So to do this, change x by 1 over detail. Do the same for z in the outer loop. For each column of blocks, we first need to get its height. So find point height at x, z. Now we need to get the block index of the bottom block in our column. So use our get grid index of position block. The y input will be 0 because we're starting at the bottom. For the x, convert from Perlin Noise coordinates to block coordinates by multiplying x by detail. Then subtract chunk x times chunk size to get from coordinates in the world to coordinates of just our 3x3 grid of chunks. But we need to subtract 1 from chunk x so we don't have any negatives, because the inputs to the generate chunk block can be negative, but our block coordinates can't be. Then duplicate this for the z input, changing x to z and chunk x to chunk z. Now with our find point height block, we've gotten the Perlin Noise height value, but we need to find how many blocks are going to be in our column. So let's create a new variable to hold that. I'll call it column height. We'll set column height here to height times height modifier plus surface height. So this is where we use some of those variables we set up at the beginning. Now there's a chance that our column is too high, as in it's higher than the height of the grid, in which case we'll set column height to grid height. Now repeat column height to generate our blocks, except I'll actually subtract 5 from this So we just start by generating the stone, so we can make room for the 5 layers of dirt and grass on top of that. Each time, we'll replace item block index of grid with 4, which is stone. Then we'll change our block index by grid width, which is what we do to move the block index up by 1. Now duplicate that for the dirt, and repeat 4 times, adding 3 to grid instead of 4. Then finally we'll add the grass, so replace item block index of grid with 1. And there you go. Shall we test it? Run the project, and you should find yourself in a lovely generated world. Try walking towards the other edge, and you'll eventually hit the end of the world we've generated. If you encounter any strange boundaries or sharp cliffs, you've probably messed something up in your chunk generation. But aha, looks like we're finally at the edge and we can jump off. Whee! We can see there's just stone down there, no bedrock. I'll leave adding bedrock as a challenge for you. But ideally, rather than hitting an edge, we should simply find more chunks. Let's code that now. Go back into your main game sprite, and in the forever loop, after we display UI, we'll broadcast and wait a new message, which we'll call check new chunk. Back in generation, we'll get a when I receive check new chunk. Here we want to check if the player is outside of the center chunk. Let's start with a positive X direction. That is, if player X is greater than chunk size times 2. Because remember, the center chunk consists of coordinates between chunk size and chunk size times 2. Now in here there's a chance that the player has gone so far that they're off the Perlin Noise grid. We can check this by checking if chunk X is greater than, and then here we need to convert the grid size variable, which is how big the Perlin Noise grid is, to chunk coordinates, which we can do by multiplying by detail over chunk size, and then we'll subtract 2 just to give a little buffer room. Now if we have gone too far, like this, then we'll set our player X back to where it was, as in chunk size times 2. So we'll just stop the player from moving any further. In the else though, if we can move further, we will first push the player back 1 full chunk, so change player X by negative chunk size. Then we'll change chunk X by 1, signifying that we've moved 1 chunk in the positive X direction. Then we'll broadcast generate chunks again, and wait, so we just regenerate our chunks at this new location. Then finally stop the script. Okay, that was the positive X direction. Let's duplicate this for the negative X direction. Here we'll want to check if player X is less than chunk size, and the player will be off the grid here if chunk X is less than 2. In which case we'll want to set player X simply to chunk size, which is where it was. In the else, well, we're moving in the negative direction, so we'll want to change player X by positive chunk size to push it backwards. Then change chunk X by -1, and again generate chunks. Alright, now we'll duplicate all of this for the Z direction. Then we just want to go through and change all of the X's to Z's. So player X will become player Z, chunk X will become chunk Z, etc. And once we've finished doing that, then we can try it out. Run the project and start walking in a direction. You should be able to continue seamlessly without hitting anything strange. If we show the chunk variables, we can see that we are in fact changing chunks. With a bit of further testing, we can see that all 4 directions are working. Wonderful! Now I think our world is looking a little bland as it is, so let's spruce it up by adding some water. Go to generate chunk at, around where we generate the dirt and grass, so that's the repeat 4, then replace item block index of grid with 1. We'll check if our column height is greater than surface height. In other words, because surface height can represent the water level, we're checking whether the stack of blocks we are generating is higher than the water level. If it is, we'll put what we have in there, and in the else case, instead of adding dirt and grass, let's add some sand. So duplicate the repeat 4, and change it to a repeat 5 because we don't have any grass to go on top of it, and replace item block index of grid with 14, which is the sand. Then we'll want to put some water on top of it. How much? Well, that's determined by the surface height, and then we can subtract from the surface height the height of the column to get the difference between the top of the surface and the top of the water level. Then each time we'll replace item block index of grid but with 8. Trying this out, let's go and find some water. And here we go, and that is looking great. You can even see that there is some sand around the edge of the water. We can add even more sand if we go back into generate chunk at and change the column height greater than surface height to a greater than surface height plus 1. So it will generate sand even if we're 1 block above the water level. Yes, that is working well. I really like how the sand is only on some of the blocks in the topmost layer of sand, which are the ones closer to the water. And this is happening because the column height variable isn't rounded. It has a decimal. But when we repeat by it, the repeat loops round its value. So sometimes it triggers the extra sand generation and sometimes it doesn't. Now let's try running the project again, and this time building a nice cobblestone pillar. Now say we leave it and move into another chunk. What happens then? Well, we would expect it to disappear, because those chunks are being regenerated when we change chunks. Sure enough, when we come back, our beautiful pillar is gone. Let's fix that. We need to save the chunks we've been in, so create a block called Save Chunks. Like with when I receive generate chunks, we will save our 9 chunks individually. So create another block called Save Chunk at with 2 inputs, x and z. Just like before, we'll use this 9 times in our Save Chunks block. First with inputs -1, -1, then 0, -1, 1, -1, and then duplicate those 3 and change the z values to 0, and again changing the z values to 1. Now in Save Chunk at, we're going to start at the corner, and we'll first get the grid index of that position. So get grid index of position. Again, the y will be 0, and the x will be x times chunk size, because we want to convert from chunk coordinates to block coordinates, except we should actually add 1 to the x, because again the x input can be negative, and we don't want that. Our grid index, or block coordinates, cannot be negative. Okay, now duplicate that for the z, changing x to z. Now we'll want to build up a code for our chunk, because we're going to store our chunk in a string. So create a variable called code. At the top of the block, we'll set code to the empty value, ready to be built up. Now we're going to repeat over every block in our chunk. So start with the z-axis, repeating chunk size, then the y-axis, repeating grid height, and then the x-axis, repeating chunk size. In the inner loop, we need to change block index by 1 each time we loop to move 1 block to the right. And then after that loop, in the repeat grid height loop, we'll need to change block index by chunk size times 2. And that is because we're skipping 2 chunks, and then we'll come right back around onto the row on top of the one we were in. Now in the outer loop, we don't need to do any changing of block index because we don't have vertical chunks, so there's nothing that we need to skip over. Now inside this loop, let's build up our code. We'll set code to join code, and then item block index of grid, then with an underscore. So we're just recording each block of the grid separated by underscores. Let's try running this block, and click on the code variable to see what our code looks like. You can see that it is very long. So let's try to shorten it a bit. One thing you'll notice is that there's a lot of repeated values. So it would be nice if we can combine all those values into 1, or rather 2. We'll record each series of the same block, by which block it is, and how many of those blocks there are in a row. To do this, we need to make 2 new variables, block, which we already have actually, so scratch that, but also amount, which I'll abbreviate AMT. So these will hold which block we're currently recording and how many of those blocks we've found. So at the top of save chunk, set block to item block index of grid. So the first block that we are recording. Then set amount to 0 because we haven't found any of those blocks yet. Now inside this loop, we'll check if item block index of grid equals block. So is the current block that we're saving the same as our block variable, which is, the previous blocks? And if it is, then we don't need to record anything. We'll simply change amount by 1, noting that there's another one of those blocks in a row. Now in the else, if we've hit a different block, then it's time to record the series of that same block that we found before. And here we need to put our set code, and then we'll set our block to the new block that we found, and set the amount variable back to 1, because, we've only found one of this new block. And now when we set the code variable, we need to set it to include the amount as well. So set it to join block underscore join amount underscore. Like so. Now at the end of these loops, we won't have recorded the final series of blocks, so we just need to duplicate our set code block one more time and put this at the end of our 3 loops. Alright, so that will give us a much shorter code, but we need a place to store this code. So let's create a list called chunk save. When I receive setup, we'll delete all of our saved chunks, and in save chunk at, we will add the code that we found to chunk save. We also need to record the position of this chunk that we've just saved, otherwise we won't know what that code goes to. So we'll add chunk x plus our x input to chunk save, and then we'll add chunk z plus our z input to chunk save. And, we're adding the x and z inputs because those are the offset from our current chunk. And now if we run this, we can see that, well, for one thing, the code variable is much shorter than it was, and the chunk save list now has 3 items in it. Now if we run this again, you'll notice that the chunk save list just gets another 3 items added to it, even though we're saving the same chunk. But there's really no need for that. In fact, we want to replace our previous save with this new save. So let's make a block to check whether we've already saved a given chunk. I'll call it check chunk save with 2 inputs x and z. We'll need to loop over our chunk save list, and to do that we need to store the index we're currently checking. So create a variable I. We'll start by setting I to 1, the beginning of the list. Then we'll repeat over the whole list. So repeat by length of chunk save divided by 3 because there are 3 pieces of data per chunk. Then each time we'll change I by 3 to move on to the next chunk. Now for each chunk we'll want to check whether its x and z values match the inputted x and z values. So we'll check if item I plus 1 of chunk save equals x, and item I plus 2 of chunk save equals z. If the coordinates do match the ones that got inputted, we can simply stop the script. What this means is that the I value will stop at the index in the list of the correct chunk, or the chunk at the desired position. Now if we go through the entire list and we don't find any chunks, we can set I to the empty value at the end, signifying that there are no chunks saved at that position. Then back in save chunk at, let's check chunk save for chunk x plus x and chunk z plus z. Then if I is the empty value, meaning that there is no chunk saved there, then we'll put our previous add to chunk save list code into there. And in the else condition, if we did find a chunk, we'll replace item I of chunk save with our new code. Now we're going to want to use our save chunks block when we exit a chunk, right before we generate new ones. So in check new chunk, before we change chunk x, let's use our save chunks block. And we'll want to do that in all 4 directions. Like so. Awesome. Now we have code to save a chunk, so let's write code to load a chunk. Make a block called load chunk with an input code text into, and then inputs X and Z. Now the code for this will be very similar to that of save chunk at. So let's duplicate that code and drag it under load chunk. We'll want to change our variable setup though. Rather than setting block, we'll set code to the code input. Then we need a new variable to hold what index of the code we're currently reading, and I'll call that read index. We're going to set that to 1 at the start of the block, and then we'll keep the set amount to 0. Now we can delete the if statement inside the inner loop. And in here we need a way to read what value is next in the code. So I'll make a block for that called read next value. I'll make a variable value that will hold what value we've read in this block. So start by setting value to the empty value, then repeat until, and then we want to repeat until we are no longer reading a number. So that is, letter read index of code is greater than 9 or less than 0. Now, if it is still a number and we're still in this loop, we'll set value to join value, then letter read index of code, then change our read index by 1. Now when we've hit something that isn't a number, we'll want to change read index by 1 after this, simply so next time we use this block we start at a number. Now back in load chunk, we'll use this block, and then the first time we do it we'll set block to value, and the second time we'll set amount to value. So we get the two pieces of data we need. Then we'll replace item block index of grid with block. However, we only want to read the next value if we no longer have any blocks to place. That is, we've placed all the blocks in the current series we've read. So we can check if amount is less than 1. And then outside of this, after we replace item block index of grid, we will change amount by -1. And yes, I did accidentally use the chunk save list here. That should be the grid list. So essentially what this loop is doing is reading values, so seeing how many of a block we need to place down. Then each time we place one of those blocks down, we decrease amount, and then once amount is 0, or in other words we don't have any blocks left to place, we read the next value to see what block we want to place next. Now we're going to use this block when I receive generate chunks. Sometimes we want to generate a new chunk, and sometimes we want to load a chunk. So let's rename our generate chunk to create chunk at. And then we'll create a new block called generate new chunk at xz, and we'll put our old generation code under this new generate block. In our create chunk block, we'll want to check whether we've saved a chunk at a given position. So we can use our check chunk save block. Check chunk save at chunk x plus the x input, and chunk z plus the z input. Now if I equals the empty string, meaning that there is no chunk saved there, we'll generate a new chunk at xz. Otherwise, we need to load chunk, and then we'll get the code from item I of chunk save into xz. Alright, let's go ahead and run that. And when we move into another chunk, everything seems fine. We don't fall off the world or anything, so that seems like a win. Of course, we need to test that our chunks actually save. So let's try building something. I'll get some cobblestone and make a little pillar here, or an arch. I'm not really sure what this is. Let's call it modern art. Anyway, when I go some distance away and come back, our beautiful piece of modern art still stands. This is awesome! Now we have an enormous world in which to build as much as we want. One thing, let's try standing over here and looking down this hill. You'll notice it's really hard to tell where the edge of each block is. It just looks flat. So let's add a darkness effect for pixels farther away from the player. head into the main sprite and go to Create Camera View. When we add Brightness Mod to View, we're going to want to decrease this value that we add for blocks farther away from the player. So let's subtract from Brightness Mod the dist variable, which is how far away the pixel is, divided by the view distance so that we get a fraction of the total view distance, and then multiply by 50 to make this effect a bit more substantial. That's a bit much, so let's go into Move Forward and change what we set Brightness Mod to. I'll just increase everything by 20, so change the -20 to 0, the -10 to 10, and the 0 to 20. Of course you can mess around with these as much as you like, but I think this works pretty well. Let's end by turning up the view distance to 12 and the FOV to 40. I think that might look a bit better. A little laggier though. Anyway, that's all for this episode. We didn't get around to adding trees, and that's secretly because I don't have a good method of handling trees on chunk borders as of right now. And it's also just a bit of a pain to code, as you have to manually specify where each of the blocks in the tree go. But perhaps you can try implementing trees as a little challenge to keep you occupied between now and the next episode. Anyway, I hope you enjoyed this tutorial. Have a great rest of your day, and goodbye!